So we have 5 speakers in the last session. And we will start with Magnus Ullner from Lund, who will tell us about simulations of osmotic pressure in polyelectrolyte solutions. Magnus.
Better? Yep, okay, good, thanks. Which gave me a reason to stall so more people can come in. Tricky, aren't I? Anyway, so osmotic pressure. So in a classical picture, we have a solution in contact with oops, I'm getting, yep, this thing. In contact with a pure solvent and then separated with a semi-permeable membrane. Because the chemical potential is lower for the solvent in the solution, for instance, by mixing entropy, there's a tendency for the solvent to enter the solution and dilute it even further. And then to counteract that, you have to have a higher pressure over the solution than over the pure solvent. And the difference at equilibrium, that is osmotic pressure. And if you have an ideal solution, then the equation of state has exactly the same form as an ideal gas. And although the osmotic pressure is actually a chemical potential of the solvent, we can calculate the osmotic pressure as the pressure of the solute, as in this case as an ideal gas, but also if there are interactions between the solute particles. So that is how we will be looking at osmotic pressure. And as I said, or as it says, the osmotic pressure is a measure of the ability of a solution to attract the solvent. And when is that important? Well, in this case, it's quite important. In diapers, we have superabsorbents, where in fact polyelectrolyte gels then absorb the liquid that sort of comes out of whoever is wearing the diaper. And exactly a very similar situation in food, which perhaps not so nice connection, but anyway. Where we have the gels, or in other case. Another case of osmotic pressure to regulate the amount of water inside and outside something is in cells. In plant cells, they have a high osmotic pressure. That is, have a higher concentration of something, and in this case, ions and other things, to attract water to expand the cells and press against the cell walls and then make the plant stiff. And we as people, then we add salt and sugar on the food in order to extract the water from bacteria and other nasty stuff that wants to deteriorate our food, to make it rot. So osmotic pressure comes in a lot of places, and I could sort of go on with the examples, but then time doesn't allow. So in any case, as I said, we can see that the osmotic pressure as the pressure of the solutes. And if an ideal solution, it's just the it's like an ideal gas. And as I forgot to mention in the previous slide here in the beginning, we can rearrange the parameters a bit to express osmotic pressure as concentration. So the concentration, and it's easy to think about when it's an ideal gas, it's just the concentration of the gas particles. Anyway, so in that case, if we have a neutral polymer, when I say polymer, I mean an uncharged chain. Then it's, in a dilute regime, it's just the concentration of the polymer. But with a polyelectrolyte, we get both the polymer, the chain itself, but the counterions. So we get a lot more particles for the same mass, so to speak. So we get a higher osmotic pressure for a polyelectrolyte. But it's not an ideal solution. We do have an interaction between the polyion and the counterions, and they attract, which kind of reduces the effective concentration. And to measure the difference between the ideal pressure and the actual pressure, we have the osmotic coefficient, which is the actual osmotic pressure divided by the ideal one. So this is sort of the general background, and we'll be looking at the osmotic coefficient. So what I've done is to perform simulations, and I've been using a metal which is basically freely jointed chain. There's no sort of angular potential. And the monomers are hard charged spheres, and so are the counterions. They are also hard charged spheres. So explicit counterions. And we have the two situations. One where we have a single chain inside a spherical cell. And is very nice because in the cell model, osmotic pressure can be measured as the concentration on the boundary. So it's easy to think about it because anything that affects the concentration on the boundary, such as attracting the counterions to the polyion, is directly affecting the osmotic pressure. So it's easy to think about the phenomenological effects. And I also done bulk simulations using GOMAX with periodic boundary conditions and multiple chains, actually 8 chains, which is more than enough to get convergence in terms of size. And then, of course, the pressure is more difficult to think about how it all interactions. But anyway. So, and the first thing we see is that we have the same trends in the cell model and in the bulk simulations, which is nice because then we can use the cell model ideas to describe the effects. There are some artifacts, and I use the classical. We see that the osmotic coefficient is slightly higher than in the cell than in the bulk, and that's because of the confinement in the spherical cell. And it also says I'm using salt-free simulations, and that is enough because there's the old empirical additivity rule, which says that the polyelectrolyte contribution to the osmotic pressure can be treated independent of the salt, so they can be added together. And also, at higher concentration, salt will be excluded from the polyelectrolyte solution due to a Donnan type effect. So we get all the interesting effects by looking at the salt-free system. We don't need the salt at this point. So here, what you see is 6 different cases at 2 different bond lengths, and there are 3 different degrees of ionization. And if we have a short chain, which is then fully charged, or have a full charge on every monomer, we have a lot of charge and they are attracting the counterions, and we get a low osmotic coefficient. But when we have a longer bond and a weaker charge, then we get a higher osmotic coefficient. And you notice here that we get parallel lines, but there are 2 different slopes for the different bond lengths, and I will come back to that. Another thing you'll notice is that there are 2 regimes. So if you start to think, we start off with an infinite dilution, so we have an infinite sphere. In that case, you will be able to dilute away all the counterions, and there are no interactions in the system, which means that it's ideal. And we would have an osmotic coefficient of 1. But as you reduce the volume, the counterions will get closer to the polyion, and they start attracting, and then sucks in the counterions from the boundary, and we get a lowering of the osmotic pressure or the osmotic coefficient. But at some point, then we start to have an increasing osmotic coefficient. And the standard explanation for this is that, okay, when we have this decrease, we are in a dilute regime, and when we have the increase, we are in a semi-dilute regime, and then the minimum here corresponds to the overlap concentration. So what does that mean? Okay, when we have a neutral polymer, in the dilute regime, it means that the polymers are far away from each other, and they only interact occasionally. So they are independent and interacting one-on-one, basically. But a polymer is a loose object. So if you think of the domain that it covers, inside domain there is a polymer concentration, and it's not concentrated. It's still dilute inside this area or volume that the polymer covers. So when the entire solution has the same concentration as this internal concentration in the polymer domain, we reached what we call the overlap concentration, because then we are actually touching, the different polymers are touching, and we're reaching the semi-dilute regime. And the idea there is that now we're starting to interacting particles, so to speak, are not just individual chains, there are segments of the chains, and there are correlation lengths. So with a higher concentration, the correlation length is smaller, and you get more particles interacting. And that means an increasing osmotic coefficient, osmotic pressure. So this is the reason why people have equated this increase with the semi-dilute regime. The problem with that is that the semi-dilute regime is a nice idea, but it's a polymer concept. And we're talking here about segment interactions. But with a polyelectrolyte, we have seen that the counterions, that the most particles in the system are counterions, so they dominate the osmotic pressure. And also we have electrostatic interactions to take into account. And you can see that directly here in the cell model. If you look at the distribution of the counter ions, which are the red, and the monomers, which are the black ones, that there are much more counter ions at the surface, which means that the counter ions actually do dominate the osmotic pressure. And even in this case, where we see we have an off-center peak of the monomer distribution, which means that we are starting to get the artifacts of the confinement of the cell. Because the chain can't sort of extend beyond, so it has to go around a little bit, and then if it still wants to be stretched to some degree, it has to sort of leave the center and go around it. So that's where we get the off-center peak. But you still don't see a lot of polymer at the surface, because the polyion don't want to stay close, because that would mean squeezing the ion atmosphere, squeezing the double layer. So it still tries to avoid the boundary. So it's not the polymer, it's not interacting directly. So you would think of this, I mean, the spherical cell would correspond to other polymers in the system. So it's not interacting directly through the segments, the polyion itself. It's interacting through the double layer. And another way to see that is to use the Poisson-Boltzmann theory, where we have it's also a cell model. And it's also easy. I mean, Rudy gave an introduction to the Poisson-Boltzmann anyway. I mean, there's no regulation here, but in this case, it still works. Anyway, so if we have an infinite cylinder, I mean, one shape is a cylinder. If it's an infinite cylinder inscribed in a cylindrical cell, we see here that it's actually continuously increasing. It starts at an infinite dilution. It has a limiting low value of osmotic coefficient, but then it increases levels, increase levels off a little bit, but it's always increasing. But if you have a sphere, which is then a finite object, we can once again dilute away the counter ions at infinite dilution, and we start with a decrease, and then we get the increase of the osmotic coefficient. So what we see here is that the decreasing effect, that is a finite size effect, while the increase is a double layer effect. And mind you, I'm not saying that the semi-dilute regime doesn't exist, or that we're not in it, or anything like that. Just saying that's not the answer to the explanation for the increasing osmotic coefficient. It's kind of irrelevant in a sense in this system. Okay, so then as a reality check, we need to compare with experiments. And what we see here is that they more or less look like the Poisson-Boltzmann cylinder. They even have the dip at low concentration, but that can also be a salt effect, because in the real system, we don't have zero ionic strength. And when we are comparing the two compartments, one with Polyelectrolyte and one with reference solution, it's not absolutely salt-free. So we can get actually, we have the same ionic strength, which is a low ionic strength case. So at infinite dilution, in this case, you would actually have zero osmotic pressure, because it's a difference between the two compartments. But that's beside the point anyway. You see also that, okay, this simple model is not too bad. Here we can also see the artifacts of the cell model for short chains, but it's almost gone for a little bit longer chains. Okay, so now how should we describe the chains? Well, the thing is that it is a linear object, so we should use parameters which are in a sense linear. And for instance, if we want to describe the size, rather than have sort of my simulations here with n monomers, I should instead use the contour length to describe the size. And instead of degree of ionization, I should use the linear charge density. And even with concentration, it should not be just the monomer concentration, it should be the concentration of contour, so the contour length of the chain divided by the volume per chain. And if you look at that, you'll see that if you take the concentration of a part of the chain, it means in a way that you're creating a cylinder around it. You can think of it as a cylinder, and the radius of that. So then the concentration is 1 over that hypothetical cylindrical radius squared, and then you have a pi in there also, but let's forget about that. For the moment, I plotted it without the pi. And then you actually see that I get parallel lines. As I said before, we have different slopes for the different bond lengths, but now they are parallel. And that is because this is a better representation, because they are sort of the same thing. I had more monomers when I had shorter chains, but the same linear charge density. But they are still different. And then the thing is that they are not the same size. So if I'm adding the short chains with the same contour length as the ones with the longer bonds, we see that red and the blue, they are basically the same at low concentrations. So they kind of, using these linear parameters, we have a general description of the different chains. However, I kind of divide the charge into monomers and things. But at high concentrations, there is a difference. So at high concentrations, local interactions start to become important, and then it becomes important exactly how you have constructed the chain as a coarse-grained model, or any model, or in any case. So I didn't mention that, but also with experiments, what you see that there's a long chain limit. There's also an old empirical rule that if you have longer polyelectrolytes, they have the same behavior. And we see that they all sort of converge to some long chain limit. The short chains, they don't have enough charge to attract as large fraction of the counter ions as the long ones, so they have a higher osmotic coefficient. But as we increase the concentration, screening takes over, and they also starting to approach the long chain limit. So now we have linear parameters, and we have a long chain limit. So then you think, maybe the Poisson-Boltzmann cylinder would not be such a bad model for Polyelectrolyte. So let's check that idea. So here comparing my simulations, my bulk simulations with the Poisson-Boltzmann cylinder, and then the simulations are the ones with symbols, and the Poisson-Boltzmann is the sort of the solid lines. And of course, at low concentrations, obviously a difference. One is an infinite object, and another one is finite, so that should be a difference. But okay, we have sort of similar slopes, but the big difference is they actually is kind of like shifted. It looks like they have sort of shifted one bond length in a sense, or one linear degree, linear charge density. So, and why is that? Well, the thing is, here I have used the linear charge density for my cylinders. But when when concentration of the polyelectrolyte is increasing, the chain relaxes. It starts off kind of extended, but then starts to relax and have more compact conformations. And we can sort of see that here. We have plotted the radius of durations. It starts off kind of biggish, and then it contracts a little bit. So in order to do a fair comparison with Poisson-Boltzmann theory, we should have recalculate the parameters to effective linear charge density. And you could think, okay, well, let's take the end-to-end distance and take that as a kind of an effective contour length and divide the number of charges, and then you get the linear charge density. Unfortunately, it's not that simple. I mean, it's more like local interactions rather than kind of the global end-to-end distance. So it is a little bit more complicated. And unfortunately, I don't have a recipe for you now, but hopefully in the future I can tell you how to change the conformational parameters into effective Poisson-Boltzmann parameters. So with that, I'll conclude and say that, well, the osmotic coefficient for polyelectrolyte system there is dominated by the counter ions. The counter ions and the polyion attracts and reduce the osmotic coefficient. For finite object, we can dilute the weight counter ions and in principle get the osmotic coefficient of 1 at infinite dilution. But when we have a higher concentration, there's a double layer effect that will increase the osmotic coefficient. And we have a long chain limit and screening and so on, which is not so surprising perhaps. And with parameters, we should use linear parameters to describe the chains, and that gives us kind of a general behavior at the lower concentrations, but high concentration, the actual way that we have modeled the chain has some effects we call local interactions. And Poisson-Boltzmann has the right sort of general behavior, but we need to rescale our parameters to have use Poisson-Boltzmann theory. Okay, with that, thank you.
Thank you
for your attention.
Couple of questions. Avi?
The initial decline, is it what is usually, do you see something like a Manning condensation?
No. Manning theory doesn't work in this case. Manning theory would predict a constant osmotic coefficient. And then it doesn't matter because I have different, you see, they all look the same, but they are both below and above the Manning limit. So Manning theory in this case doesn't help to think in terms of condensation.
Okay.
Quick question.
Yeah, you didn't say anything about the case when you have the presence of divalent or multivalent ions, but I'm sure you have something to say about it.
It looks the same, more or less. I mean, with divalent, I haven't done the high. You still have this two.
But the discrepancy between Poisson Boltzmann and the simulations will be larger.
Okay, yeah. Forget about the Poisson Boltzmann. I just talk about the simulation results. Yes,
yeah, because
and then you get the two different regimes in that case also. So they are quantitatively different, but the qualitative effect is similar in that sense.
Yes, but it's a case where Poisson Boltzmann
that doesn't work.
Breaks down qualitatively even.
Yeah, I agree. Yes, that's true.
Okay, let's thank the speaker once again.